Hello, welcome to Math 251 Calculus 1 here at Cañada College. My name is Lapuz and I'm the instructor for the course. In this video, we will take a quick overview of section 4.3, where we're going to study maximums and minimums. The idea behind this is to define extremas. Extremas are going to be our quick, short way of saying maximums and minimums, and maxima and minima, I guess, would be the plural version of that, and extremum would be singular, extrema would be plural. So we're going to define both absolute and local extrema. We're going to explain how to find critical points via definition, and we'll take a look at critical points over a closed interval, and we're going to use critical points to try to find our local max and mins. So first, the definition. The idea behind the absolute max-min is to take a look at what's happening over an actual interval, and within that interval you can define an absolute maximum or minimum. Now the definition here is that it says that there's going to be an absolute maximum at the point x is equal to c within the interval. It's an absolute maximum if you put c into the function, and regardless of any other value you put in for x into the function, the f of c is always going to be bigger than or equal to f of x for all the other x values that you can think of that's within that interval. And then the absolute minimum is saying the opposite. And it says that when you put c into the function, it's going to be less than any other x that you put into the function. Okay. So if it's a maximum or a minimum, we'll call it an extremum. Now, here are some examples of ideas within closed or open intervals. So if we're looking at from minus infinity to infinity in our first example here, x cubed, it has no maximum or minimum because the long run behavior or the function just goes up as x goes positive infinity and goes down as x goes to negative infinity. In our second example here, in graph B, we have, it looks like a maximum that pops up right in the middle here when x is equal to 0. But as you go to positive or negative infinity, it approaches 0, but never touches 0. And so it'll never have an absolute minimum in that case. Our cosine function here in graph C, we can see that there are an infinite number of maximums and minimums for the graph, and you can see the maximum happens at positive 1, the minimum happens at negative 1. In graph D here, we have a piecewise function that's defined from 0 to 4. Now, we can see that if we look at it, just scanning it from top to bottom, the largest value hits at 2. That happens when x is equal to 0. But if we keep going down, it looks like at negative 2, a y value of negative 2, there's an open circle when x is equal to positive 2. And because that circle is open, it'll never attain that minimum value, so this has no absolute minimums. For part E, for graph E, we have a value at 1, 1. It dips down to 2, 0, and it goes back up at 4, 4. So it looks like this has a maximum at 4 and has a maximum value of 4. And then it looks like it has a minimum value at x is equal to 2 where the minimum value is 0. And here in our last example, at 0, 0, we have a minimum value, but then this thing keeps going up forever. And so it has no maximum value. So there's a lot of scenarios that can happen here depending on the type of interval we're dealing with. But it turns out that if we do have a closed interval and things are continuous, then we're going to find our maximum value. And that employs the what we call the extreme value theorem. So the extreme value theorem tells us that as long as f is continuous, over a closed boundary, so this is important that we have to have a closed boundary from A to B, then we're gonna be guaranteed to attain both a maximum and a minimum, and that would be an absolute maximum and an absolute minimum. So let's take a look at these graphs again and see which ones actually apply. we have to have a closed interval. So the first graph of x cubed doesn't work because we're going from minus infinity to infinity. So the second graph doesn't work either. And remember, this theorem guarantees a maximum and a minimum. And for those two first examples, we don't have maximums or minimums. For part C, we can't apply the graph or the theorem either because it's still going from minus infinity to infinity. For the fourth graph, graph D, that doesn't apply because our function is not continuous. So if the function is not continuous, then you can't use this extreme value theorem. And F, the last graph, doesn't work either because we're closed on 0, but as we approach x is equal to 2, that's an open interval. So the only thing where the extreme value theorem works in these examples would be graph E, where you actually have a closed interval from 0 to 4. And if you have a closed interval and the graph is continuous, then you're guaranteed a maximum and a minimum. So in this case, our maximum is at 4 and our minimum is at 2, where the minimum value is 0. Okay, now beyond the idea of absolute max and mins, we're also going to look at local max and mins. So here, instead of looking at an actual interval, we're going to look at things that are close by the particular point. So here the definition says a function f has a local maximum at x is equal to c if there exists some open interval, and that open interval can be as small as you want it to be, so that f of c is going to be bigger than any f of x value regardless of what value that we pick within that small interval. And local minimum is defined to be the same way. And so here we're studying the idea of local. Local stuff means that's near a particular point. So in studying local maximums and local minimums, and also in general maximums and minimums, we're going to define this thing called a critical point. So a critical point within a domain of a function is going to be a point where either the derivative is equal to 0 or the derivative is undefined. So this undefined portion of the critical point is what a lot of people kind of forget about. They say critical point is when the derivative is equal to 0, but it also happens when it's undefined. And the critical points are important for us because they could be the places where we can find maximums and minimums. And so in the first three examples, the top three graphs over here are when critical points are happening where either the derivative is 0 or the derivative is undefined. You have yourself a maximum or a minimum. But you have to be careful. There's this theorem called Fermat's theorem that says if you do have a maximum or a minimum, then you have a critical point. However, just because you have a critical point does not mean you necessarily have a maximum or a minimum. And our last two graphs illustrate that, where we do have a critical point, both examples where the derivative is equal to 0 or the derivative is undefined. But as you can see by the graph, they are neither maximums nor minimums. They are neither a local extrema for us. And so we have to be able to test that, and we'll do that testing in a couple of sections from now. And so finding the absolute max and mins over a closed interval using the extreme value theorem is going to be helpful for us. Once we've defined our critical point, we can find absolute max and mins. And we actually have an algorithm here, a problem-solving strategy. And so first what we do is we evaluate the endpoints. Because this is happening on a closed interval. Remember, that's the only time we're guaranteed max and min. So here's our strategy for finding max and mins over a closed interval. We'll put in the values of closed intervals because the maximums and minimums can happen at the endpoints. And then we'll find critical points in the middle between A and B. And then what we want to do is we want to evaluate those critical points at the function also. And so between the endpoints and the critical points, we just have to figure out which is going to give us the largest value and which is going to give us the smallest value. And those will be our absolute maximums and minimums within that closed interval. And remember that we're guaranteed a maximum and a minimum within these closed intervals. And so this is how you would be able to find them. Okay. That's our quick overview of max and mins. We'll dive more. There's going to be more information about maximums and minimums, and we'll see that when we start looking at using derivatives to figure out the shape of the graph. Okay, good luck.